The most common elements used in organic chemistry are in the top right of the periodic table: carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those show up the most. And so it's useful to have a sort of shorthand to know how many bonds those elements can form. Carbon is in group 4A, so if you were going to draw the Lewis dot structure, you would draw carbon. It has 4 valence electrons, so 1, 2, 3, 4, and that means it can form 4 bonds. And so you can see that that is represented in this table above as something just to remember, a quick shorthand. Carbon can form 4 bonds. Okay, if we do a similar thing for nitrogen, nitrogen is in group 5A. If we wanted to draw the Lewis structure, that symbol represents the nucleus and all the inner electrons. Nitrogen has 5 valence electrons, so 1, 2, 3, 4. Only after you have 1 on every side do you start to pair them. So that's 5. And so nitrogen can form 1, 2, 3 bonds. And that's what you see summarized in this little shorthand table there. Nitrogen will be able to form 3 bonds. And it'll have that one lone pair there. Oxygen. Oxygen is in group 6A. So if we wanted to draw the Lewis structure for that, we'd draw the symbol that represents the nucleus and all the inner electrons. It's in 6A, so there are 1, 2, 3, 4, 5, 6 valence electrons. Notice I put 1 electron on each side of the oxygen before I start pairing them, and I never put more than 2 electrons on a side. And that's the Lewis dot symbol for oxygen. There are 2 unpaired electrons, and so oxygen can form 2 bonds, and you can see that that's represented in that table there. Last but not least, the halogens, and we could choose anything in this row. Maybe just because it's a little more common, let's choose chlorine. So if you had a chlorine atom, chlorine is in group 7A, so 1, 2, 3, 4, 5, 6, 7. Notice there's only 1 unpaired electron here, and so chlorine really only gets to chlorine really only gets to form 1 bond, and you can see that represented here. Now they're using a symbol here. They use X. X represents any of the halogens. The halogens are in group 7A, so here let me highlight these. Everything in yellow here is a halogen. So fluorine, chlorine, bromine, and iodine. Those are represented by that X there. That's going to be a recurring symbol throughout organic chemistry. Okay, so those form just 1 bond. And last but not least, a really common one is hydrogen. Hydrogen just is in group 1A. It only has 1 valence electron. It's unpaired, so hydrogen also can only form 1 bond. So it's useful to have these, the number of bonds that an element can form memorized, because it allows you to draw molecules a little bit more quickly. So here what they're giving us is the molecular formula, the number and the type of each atom in the molecule, and they're asking you to draw the Lewis structure for the whole molecule. And to do that, you would want to draw the first step would be to draw each of these atoms with the number of bonds it can form. So for example, we have 2 carbons. Each carbon can form 4 bonds. So I would draw carbon twice with the 4 bonds there. Then we have 6 hydrogens. And so I would draw 6 hydrogens, each with just 1 bond. And once you have all of those drawn out, you can start putting them together. Now you want whatever elements form the most bonds, so for the carbons here, you want those to be in the center, and you want to make their bonds line up. And you want to do that until all of the bonds connect to another atom. So here you can see how all of those bonds can line up to produce that molecule, and that is what this C2H6 would look like. Let's try a similar thing with the next one, B, C2H4. We have 2 carbons. First, draw the 2 carbons with the number of bonds they can make. Carbon can form 4 bonds, so we'll have 2 carbons, each with 4 bonds. And then, actually let me just fix this. Okay, then we have 4 hydrogens. 4 hydrogens, so we can draw 4 hydrogens. Now, you could put I'm lining these hydrogens up in a specific way, and you might be wondering, how do you know to put them in that specific way? You don't have to, you can just list them to the side if you prefer, but the point is that you want to ultimately have all of these bonds line up with other bonds in the molecule. Okay, so once you have all those drawn out, you take the elements that have the most bonds, so here that's carbon, and you put those in the center. So you line those bonds up. Now if we start lining up the bonds to the hydrogens, we will see that this does account for some of the bonds, but it doesn't take care of everything, because we still have these 2 bonds in the bottom that are just going into empty space. And so we don't have any other atoms for those to connect to, so what we can do is we can move those to create a second bond between the carbons. Oops. Let me actually use. We can take those 2 lines and we can use them to make that second bond between those carbons. So you sort of swing them up so they line up with each other. That gives you a double bond, and that gives you this molecule with all the bonds connecting atoms. That molecule is called ethene. It's a plant hormone. That's the hormone that makes all fruit ripen. For C, we have 2 carbons. First step, we know carbon forms 4 bonds, so we draw the carbons with the 4 bonds. And then the next step, we have 2 hydrogens, so we can draw the 2 hydrogens. We know hydrogen only forms 1 bond, so we have those. Now we're going to put the elements that have the most bonds, here that's the carbon, in the center, and we'll try to pair up as many other atoms as we can. So this is what we have, but we have a whole bunch of other bonds here that are just pointing into outer space. So what we can do is swing these bonds over. Notice these top bonds, if I make them horizontal, could line up with each other. So that would give us another bond between the carbons. And notice these bottom bonds, if I swing them up, can overlap with each other, and that would give us another bond between the carbons. And so this would be the structure for this molecule, C2H2. There's a triple bond between the carbons. This molecule is called acetylene. It's what's used in welding torches. How about for D? All right, we have 3 carbons, so we'll draw those 3 out, and we know carbon can form 4 bonds. So we'll draw those bonds around it. And we have 8 hydrogens, so we can draw 8 hydrogens. We know hydrogen only has 1 bond. It's in group 1A, so it has 1 unpaired electron. And once we have all those drawn out, we can take the elements that have the most bonds. Those are going to be in the center, and we can make their bonds line up. After that, we can take care of the hydrogens, make sure all of the bonds, as many bonds as you can find, are connecting atoms. And you can see that when all the bonds have lined up so that they connect atoms, you're left with this molecule. This is propane, which they use in gas grills. All right, here in this next one we have 3 carbons, so we'll draw those 3 carbons out. We know carbon can form 4 bonds, so we'll draw the 4 bonds. And we have 6 hydrogens, so we'll draw those 6 hydrogens out. Okay, so once you have them all drawn out, you can take the atoms that have the most bonds, that's the carbons, and you can connect them with each other in the center. Those are going to be the central atoms. And then try to make as many bonds line up as you can. So all the bonds should be connecting atoms. And notice, if I do this way, I have two bonds on one atom that are just going out into space. And I can't connect them to one of the carbons next to it because there's no room. This carbon already has 1, 2, 3, 4 bonds. So this arrangement doesn't work. I need to connect the hydrogens differently. So notice if I bring this hydrogen here, if I move that over, and then move this over, I can take these two other bonds, this bond here and this bond here, and I can swing them over so that they line up with each other horizontally. I know that looks a little awkward in 2 dimensions, but remember these are 3-dimensional structures that are constantly twisting and rotating. So you can swing these bonds however you want, just so long as they line up with each other ultimately. So here, all the hydrogens have 1 bond, the carbons have 4, all the bonds connect atoms, and so that would be that structure there. And last but not least for this one, we have a carbon, so that has 4 bonds we know. We have 1, 2, 3, and then another 4 hydrogens. So let's just put these off to the side. 2, 3, 4. And then we have an oxygen. And oxygen, if you recall, has 2 bonds. It forms 2 bonds. So we'll draw that oxygen with 2 bonds. And we might as well draw in the lone pairs. Those will become important in future chapters. So once you have all of the individual atoms drawn out, you'll connect the atoms that have the most bonds together in the center. And once those are done, fill in the hydrogens as best you can. Here, all the bonds line up, and so we are left with this molecule here. And that's actually methanol. That's what's responsible for people going blind when they drink, when they sometimes drink moonshine. So the general procedure here is to remember these shortcuts for the number of bonds the most popular elements in organic chemistry can make, draw those out for as many elements as you have, and connect them until all the bonds are not just pointing out into space, but connecting different atoms.